So, in this part of the chapter, we're going to be talking about kinetic molecular theory. So, remember what a theory is, it's an explanation to a set of observations or laws. So, we've talked about a number of laws up into this point in this chapter, the ideal gas law, Boyle's law, Charles' law, the combined gas law. So, essentially, all of those laws predict some type of outcome. We know Boyle's law, where pressure and volume are inversely proportional. So it's kinetic molecular theory that explains why these phenomena occur and why those predictions hold up. So kinetic molecular theory has five basic postulates, or essentially assumptions, when talking about gases. And so those postulates are here, that you can read. So the first assumption or postulate that we make about gases, so we can apply these assumptions to our ideal gas law, are that molecules in the gas phase are constantly in random motion, and that the space occupied by the molecule themselves, so remember when you have gas particles in a container, that those molecules actually have a volume itself. Those particles exist in space because it's a type of matter. But what kinetic molecular theory says is that the space occupied by the molecule is negligible. So essentially, it assumes that the gas particles have no volume. Particles have no volume. So all of these assumptions that we're making makes up the ideal gas law. And this will perfectly pair wonderfully with the next section of this chapter, which are real gases. Real gases are gases that break down or don't follow some of these assumptions that we make. And you'll see why soon. So the third postulate is that attractive or repulsive forces between the molecules themselves are also assumed to be negligible. And we'll see how, when we talk about real gases, we look into that postulate a little bit deeper. Also, in kinetic molecular theory, or KMT, we also call it KMT, that molecules collide and energy is transferred between molecules in the collision, but do not change the average kinetic energy of the sample. So these are completely elastic collisions. So you can think of perfectly elastic collisions like billiard balls. When they smash into each other, there's a transfer of energy where no energy is lost. And so all of it remains kinetic energy. And then finally, the last postulate is that the average kinetic energy of the sample is directly proportional to the temperature in Kelvin. So at a specific temperature, any given temperature, molecules of any gas will have the same average kinetic energy if you compare different samples. And so we know from a physics standpoint, kinetic energy is directly related to speed of substances, because we know kinetic energy, it's the energy of movement, equals 1/2 mass times velocity squared. So now, since we're thinking about kinetic energy of gaseous samples, let's think about speeds of gases at different temperatures. Since we know, because of the fifth postulate, that kinetic energy of our sample is directly proportional to the temperature in Kelvin of that sample. But so you might think, if we inspect our kinetic energy equation from first inspection, you might think, okay, all at a certain temperature, all of the gas particles will be moving at a certain speed. But that's not quite the case. In a gaseous sample, there's lots of different particles, and they're actually all moving at different speeds. But the average, if we take the sum or the average of all of those speeds, is related to the average kinetic energy. So what this slide is saying is that individual molecules in a gas sample are actually traveling at different speeds and have specific individual different kinetic energies. But if we look at the distribution of individual molecules and the speeds that they're going for different samples at different temperatures, we see that it looks a little bit different. So what you see in this graph right here are the distributions of molecular speeds of the individual particles at different temperatures. So we see the leftmost curve essentially is a colder sample. It's at 100 Kelvin. And so we see this distribution of speeds of molecules. If you would actually measure the speed of every single individual molecule, you would see a distribution like this, where most of the molecules are, I don't know, about going 200 meters per second. But what you see here on the high end of things is that there's kind of this tail that goes out, where at this specific temperature there's a handful of molecules going above 500 meters per second. And you see how this phenomena, this tail end of the curve, gets a little bit bigger as we increase our temperature. So if we look at this 500 Kelvin distribution, so we see how the most probable speed is different at 500 Kelvin than it is at 100 Kelvin. Obviously, these speeds are different. And so the most probable speed, which is the top of the curve, is much, much higher than it is at a colder temperature like 100 Kelvin. But what we also see in this phenomena is that at 500 Kelvin, this tail end, there's some molecules, a handful of molecules going over 1,000 meters per second. And so in this region, you get a point where you can have a maximum speed of a particle within your gas sample at this specific temperature. And so if we increase our speed, or sorry, our temperature of our sample even more, let's say, 1000 Kelvin, you see how the curve flattens. And so we get a much larger distribution of speeds in our gaseous sample. And a lot of them are going, very quite fast, but some of them are still going slower as well. But overall, you see that the most probable speed is higher, a higher velocity than it is at lower temperatures. So how we come up with this graph, all of these different distributions of molecular speeds at specific temperatures, comes from the Maxwell-Boltzmann equation. So that's what these curves are. They're Maxwell-Boltzmann distributions of molecular speeds in gaseous samples. And so this is the equation for the Boltzmann distribution. I'll never ask you to memorize this equation, but I want you to understand what it means. So essentially, here's a reproduction of another curve, of a gaseous sample at, let's say, 300 Kelvin. So there's two different points on this curve that I want you to understand. So I already talked about the top point of these graphs, and see how as you go to higher temperatures, the most probable speed, or the top of the curve, starts to shift to higher velocities. So we would think that this might be the average speed of the molecule, but it's actually not. This top point is the most probable speed of a molecule at 300 at this particular temperature, where the average velocity of a molecule is in this sample at a specific temperature is actually slightly right to the high point of the curve. And the reason the average speed of a molecule is slightly to the right is because of this little tail that I talked about earlier. So this tail kind of just bumps up the average slightly to the right, or slightly higher, to the topmost curve. So there's 2 points that I want you to understand. The most probable speed, which is the peak of your Maxwell-Boltzmann distribution curve, and then our what this is mu RMS, so our root mean squared speed. So this is related to our average kinetic energy of our sample. And so how this value is calculated is if you take the kinetic energy, the average kinetic energy of your sample, and plug it into our regular, kinetic energy equals 1/2 mass times velocity squared. What this velocity is the calculation of the root mean squared velocity. And so you are calculating this velocity. You're not calculating the topmost point velocity on this graph. You're actually calculating this value. So we have an equation to relate the root mean squared velocity of a molecule or a particle within your gas sample directly to temperature, because I might not give you, the kinetic energy of the sample in joules. Typically, when we think about gases, we think about the temperature of those gas samples. So temperature is a measurement of average kinetic energy of a sample. And so how our root mean squared velocity is related to temperature is through this equation. And you'll always be given this. Well, I guess the final is open notes, so no big deal. But the root mean squared velocity of a particle within your gaseous sample is, again, related to temperature. And that's for two reasons, because we know that the average kinetic energy is equal to 1/2 mass times the average velocity, or root mean square velocity squared. And we also know that kinetic energy and temperature of your sample are directly proportional to one another. And so that's how we get this equation. It comes from the Boltzmann distribution, doing some mathematical manipulation to it. So remember, the root mean squared velocity is related to the average kinetic energy of the sample, which is then related to the temperature of that sample. And so the equation for that is the square root, that's why it's called root mean squared, um, square root of 3 times r. This r is a different r than our gas law r that we've been using. This r that we want to use is actually 8.314 joule over Kelvin moles. So just make sure temperature is in Kelvin here. So make sure that you're using the correct R value here. And you'll see how the units won't cancel correctly if you use the other R constant. They're actually the same number. It's just we change the units, and there's a little bit of unit conversion. So this is still the ideal gas law constant. It's just a different one with a different unit. So 3 times R times temperature in Kelvin, must be in Kelvin, over the molecular weight of your sample. So we can only calculate root mean squared velocities for pure samples. And so because of the unit of joule, a joule is a kilogram meter squared over second squared, we need to make sure that our molecular weight is actually in kilograms per mole in order for it to cancel out with a joule. And that's a consequence of SI units in physics. So just make sure if you use this equation that molecular weight is in kilojoules per mole to get all those units to cancel out. So let's look, actually calculate a molecular speed or a, root mean squared velocity of a sample. So this question says, what is the speed of a chlorine molecule with the average kinetic energy at 20 degrees Celsius? So what you should identify here is that we want a speed at an average kinetic energy. So when we calculate speed from average kinetic energy, we are actually calculating root mean squared velocity. So we want to use that equation. So if we write that equation, it's root mean squared equals square root of 3 times r times temperature over your molecular weight or your molar mass of your substance. So the molar mass of chlorine is 70.90 grams per mole. All right. So really all this is a plug and chug, but we want to just make sure that we put in the right units for everything. So let's plug in those numbers. So 3 times R, but R has to be this different R, 8.314. 8.314 joule Kelvin mole times temperature, but temperature needs to be in Kelvin. So 20 degrees Celsius plus 273 equals 293 Kelvin. So 293 Kelvin over molecular weight. And so I gave it to you right here. It's 70.90 grams per mole, but because of the unit of a joule is equal to a kilogram meter squared over second squared. So we have to convert grams per mole to kilograms per mole. So that's just dividing the molar mass by 1,000. So I'll just do that here in the problem. So 70.90 grams per mole over 1,000 grams gives you 1 kilogram. And so those units will all cancel out. And so if you stick all of these values in your calculator and take the square root of that, you'll get that your root mean squared velocity is, I have it right there. So 321 meters per second, or about 700 miles per hour, to put it into perspective. Let's think of a more conceptual question here. So we just calculated the root mean square velocity of a chlorine sample at 20 degrees Celsius. But how would the root mean squared velocity change if we had a lighter molecule in the same sample conditions, like hydrogen gas? So how would that be different if it was at the same temperature and we were calculating the root mean squared velocity? So if we look at this equation for the root mean squared velocity, which is related to kinetic energy, the values that we put in, 3 is it's just a value. R is a constant. So the numbers that we put in are temperature and molecular weight. So I said at the same temperature. So obviously temperature in both of those calculations would be the same. I don't want you to actually calculate it. Let's just kind of think about it. If we had hydrogen gas in that sample, then our molecular weight would be different. So the molecular weight of hydrogen gas is about 2 grams per mole, while chlorine gas is 70 grams per mole. So I would predict if we would put a lighter molecule in the same sample conditions that our root mean squared velocity would be faster. Oh, I have that here. A lighter molecule would have a greater root mean square velocity because our molecular weight value appears in the denominator. And so in both of these samples, the kinetic energy is the same in the sample. But what's different is how fast the molecules are moving, and that's due to the masses of the particles themselves. So how we can kind of think about these Maxwell-Boltzmann distributions based upon different molecular weights of species, if we have different substances in our balloon but under the same conditions, meaning like the same speed. So this graph shows different different samples, different noble gas samples, all with the same average kinetic energy. They're all at the same temperature. So at same temperature, meaning that they have the same kinetic energy. But what you see is that the Maxwell-Boltzmann distribution changes for these different species. That helium, because it's the lightest molecule of all of these, helium has a much larger distribution, that a lot of its molecules, the particles in that gas sample, are actually moving faster than xenon, which is the heaviest. So these numbers here are the molecular weights. Xenon is the heaviest noble gas, and so you see that the distribution curve shrinks, and so those particles are not moving as fast in the sample at the same temperature as like a helium sample. And so essentially what you're seeing in this graph is that the lighter the sample, or the lighter your molecular weight of your molecule, the faster the speed is for that molecule. I mean, if we're comparing root mean squared velocities, you can see the lighter it is, the more up there, xenons is like right there. The faster that they'll go. And the heavier molecular weight molecules will be moving slower. But in all the different graphs, the kinetic energy of the samples, the temperature of the samples are the exact same, but their graphs look a little bit different. So how else can we use kinetic molecular theory to answer some problems? So if we look back at the first postulate of kinetic molecular theory, we say molecules are constantly in motion. So one topic that we can bring up is diffusion of gases. We experience diffusion of gases on an everyday basis. It's like if I open up a perfume bottle in the corner of the room, eventually everyone will smell it. It might take a couple minutes, but eventually everyone will smell it. Or if there's like a bakery down the street and they're, baking wonderful smelling breads, eventually you will smell it down the street or on the sidewalk or something. So, in this previous question, we talked about the root mean squared speed of molecules. They're going really fast. They're going, 700, hundreds of miles per hour. So you'd think if I spritzed a perfume bottle and I just told you it took a couple minutes for you to smell it, like if I just spritzed it in the corner of the room and it took a while to get to you. But I just said that the speed of these molecules are going really, really fast. So shouldn't you smell it instantly? Well, that's where diffusion comes into play. So we know that gases are traveling at hundreds of meters or miles per hour, but why does it take so long for a molecule to get from one side of the room to the other side of the room? The reasoning is because diffusion, when gases make it go from point A to point B, it's slowed down by collisions with other molecules or the walls of the container. So typically, when I spritz the bottle and we count how long it takes for you to smell it, we're looking at the net distance traveled of the gas molecule. But if we look at the actual path that the molecule takes to get from the corner of the room to your nose, it's actually going crazy. It's going everywhere. It takes a much, much longer path in order for it to get to the end. So the average distance a molecule travels before it actually collides with another molecule and changes directions is actually really, really small. That these molecules are constantly moving and they're constantly hitting other molecules. And so this brings us to something that we can actually measure. So it's kind of difficult to measure diffusion, but we can measure effusion. So effusion is a similar process, and it's not as complicated by collisions with other molecules. So effusion is a process in which a gas molecule escapes its container to another container via a pinhole. This is something, the rate of effusion is something we can actually measure. So molecules can escape with the same speed that they had in their container, and that is proportional to the temperature of your sample, which is also related to the average kinetic energy of your sample. So essentially, how fast particles are moving is essentially how fast molecules, gas particles will escape through that pinhole. Essentially, we're like looking at the walls of the container and how often it's hitting the walls of the container. If one of the walls of the container is just a small pinhole, we can actually measure that rate where those gas particles are escaping. So here, our main picture here is that our root mean squared velocity of a sample is directly related to our rate of effusion of a sample. So the faster those particles are moving, the more they're bumping into the walls of the container, the more often a particle will go out the pinhole of that container. So a calculation that we can actually do relating to effusion is relating two different gases at the same temperature. So in this picture, you see two different balloons. You see a balloon containing just pure nitrogen gas and another balloon containing pure helium gas. So if I just take put a small hole in each of these balloons without popping the balloon. So we just put a small hole in them, and let's say they have the same amount of gas in it. What we'll see is that the lighter gas, so helium, actually effuses or deflates faster than the diatomic nitrogen sample. And that is because the root mean squared velocity of helium is greater. So this is great, I guess, higher. So these are going faster. I'll write that. So helium is moving faster than nitrogen, so it's slower. And the reasoning for that is if we compare the molar masses of these two substances. Diatomic nitrogen has a molar mass of about 28 grams per mole, while helium is what, like 4 grams per mole? So again, we're looking back at those Maxwell-Boltzmann distributions. Helium is a lighter molecule, so it's in its denominator, its molar mass it's a smaller number, so its root mean squared velocity is faster. So molecules are colliding with that pinhole at a much greater rate, and so that's why you see that the balloon for helium deflates faster than our nitrogen counterpart. And so what you see here up here is our Graham's law of effusion. So it's a calculation that we can do to relate two different gases and how fast they effuse at the same temperature. So what you see here is that the rate of effusion of substance A over the rate of effusion of substance B is equal to the square root of the molar mass or molecular weight of B over A. So what you see here is essentially our molar mass is inversely proportional to root mean squared velocity. But we already knew that. Also, we can say that the rate of effusion is directly proportional to root mean squared velocity. So you can see with these two relationships that molar mass of our sample is also inversely proportional to our rate of effusion. And so this is how we can come up with Graham's law. So the important thing to note here is if you look at the two rates, if we're looking at the ratio of rates and we do A over B, when we take the square root of the molar masses, it's then B over A because it's molar mass is inversely proportional to rate of effusion. So I just want you to note that this is not a mistake, that they're switched on purpose because rate and molar mass are inversely proportional to one another. So let's do a quick question that kind of uses Graham's law in a calculation. So we have a tank containing equal numbers of moles of HF gas and HBr gas, and it develops a pinhole leak. So our question is, what is the ratio of the initial rate of effusion of HF to that of HBr? So we want to know how much faster does HF effuse out of the gas tank than HBr. And then I have the molecular weights here. So yeah, I kind of already said it, but which molecule travels faster? Which molecule has a higher root mean squared velocity? So I would predict HF, because it has a molar mass of 20 versus HBr has a molar mass of like 81, that HF should effuse faster than HBr. And that's because its molecules are moving faster. HF is moving faster, so it's effusing faster. So if we just plug in these numbers to see the ratio, so we want to know what is the ratio of initial rate of effusion, we're essentially calculating this whole thing, the whole ratio here. And so all we have to do is take the square root of the molar mass of HBr over molar mass of HF. So that's 80.91 grams per mole over 20 grams per mole. And so you see a ratio of 2.01. So essentially what that means is that HF will effuse twice as fast as HBr when that tank develops a pinhole. And all it is just the ratio, the square root and the ratio of the two substances that we're comparing, the molar masses of the two substances we're comparing.